Hello everyone, and welcome to our course on the RayCasting technique. Thanks for joining me. My name is Gustavo Pazzi. I am a university lecturer here in London, and I usually try to integrate and embed this RayCasting project in one of my undergraduate modules at the university. And I always have really good feedback from students because this is the first time that they start to get their feet wet with these ideas of computer graphics, rendering this projection. So if you ever read anything about raycasting or ever Googled anything about raycasting, right? And chances are you did, right? If you are here watching our video, you know that we are going to create this little fake pseudo 3D projection effect, the one that you can see here on the background. As a professor, one of my favorite things is to use these very basic computer graphics techniques to teach the mathematics that you need to create these little details. Right? Students arrive in this course and sometimes they have been hurt by the mathematics during elementary, high school. So one of my goals with this course is to teach you all the trigonometry that you need, teach you all the little basic mathematics ideas that you need to go and create images like this one. And of course, right, not just this one, you're probably going to have textured walls, you're probably going to have this whole idea of smooth animation going on, a player moving around the scene, and all the mathematics, all these animation effects, the projection. We are going to learn how to develop all these ideas in our raycasting course. So if I just move here to this slide right here, if I have to summarize, right, very concisely what raycasting is, raycasting is this idea of we start from this 2D representation of our scene, our world, and then based on these 2D ideas, right, of a player moving around this little grid maze. Do you see how our player is shooting rays? So we have this field of view angle of opening, and those rays that we are casting, they are going to give us information about the distance of the little columns of the walls. And based on that distance, we can go ahead from this 2D, we can create this fake 3D projection world that we can see here in the bottom. Of course, right, this thing that you're seeing right here is a very vanilla, plain example of a raycasting, right? You can have textures, you can have the ceiling, you can have the floor, you can have sprites. There are several things that you can add to your raycasting engine, but the whole math behind going from 2D to this fake 3D projection, this is what we're going to cover in the first part of our course. And this image right here is a very good example. You can see the 2D representation of the world on the right, and you can see our player moving around and rotating, the rays being cast from our player, and on the left, you can see the result, right? This fake 3D projection that you accomplish by casting those rays and getting that information of the distance of the rays with the walls. I think that's a very good high-level example of what is the goal that we're trying to achieve with our course. Right, so we are going to achieve this whole animation, this whole projection, and understand all the mathematics that go behind this process. Right? Just before we continue, I think it's almost impossible to talk about raycasting. And if you ever read about raycasting before, chances are that this is the image that really clicks on our mind. Right? So Wolfenstein 3D, that is usually the idea of raycasting and Wolfenstein 3D, right? This 1992 game that was released by id Software. This was the first time that we really got immersed in this idea of this whole map, this movement, this animation being used in a game, right? So 1992, I think for me it was 1993 or 1994. I think that was the first time that I got my hands on a floppy disk with Wolfenstein 3D, and I just installed it on my 386 computer back in the day. But the impressive thing is, 1992, John Carmack, right, which was the developer from id Software that developed the whole mechanics and the whole idea of using raycasting for Wolfenstein 3D, the machine that they were targeting was a 16-bit 286 machine. And Wolfenstein 3D ran on a computer that had 12 megahertz. And even more impressive, right, all the mathematics and everything that he developed was using no floating point arithmetic, right? So the processor didn't have floating point abilities. All we have to do was this integer computations to achieve this effect right here. So you will see that throughout this course, I will try to be faithful to the algorithms and the whole techniques that were developed by Wolfenstein 3D. So I'm going to use almost like the same ideas that John Carmack used to get all the mathematics and get this fake 3D projection on the scene. Right? So we're going to have a map, we're going to move around, we're going to render real time our scene and achieve the whole raycasting effect. Right? So that is the whole idea. If you look at the details, you have the walls, you have all this projection going on, this idea of depth, right? So you have these ideas of this kind of 3D, there is this Z component, right? This depth in the scene, but you will see that all we're going to do, we're going to achieve this effect by using some very simple techniques of casting rays, getting that distance, and then rendering our walls pixel by pixel. So what is the plan, right? Let's look at the learning outcomes and the step-by-step of what I have in stock for our course. First things first, I am going to give you this kind of very high-level idea of the raycasting technique. So what are we trying to achieve? What is the step-by-step that we're going to follow to get to our end result, right? So a basic introduction, we spoke a little bit about the history, but we're going to have a basic introduction on the whole raycasting techniques. And the next thing that we're going to do will be a basic trigonometry review, right? Don't get scared, right? Don't worry too much. Whenever I say trigonometry review, I just need everyone to be on the same page when it comes to the mathematical terms and the jargon that I'm going to use throughout the course. So whenever we are implementing our raycasting engine, I'm going to talk about angles, I'm going to talk about distances, I'm going to talk about things like cosine and sine and tangent. So we are going to review all these ideas. And I will try to make things as interesting as I can, right? This is one of my pet projects here at the university. I always try to add a little bit of mathematics in game development and programming. And I always get good feedback from students. So even if you think you are comfortable with these ideas of basic trigonometry, sine, cosine, if you think you know everything there is to know about these things, I would suggest you to watch the little trigonometry review because who knows, right? Maybe you learn something new. And as I mentioned, the important part is I want everyone to be on the same page when it comes to the terms and the jargon and all these little ideas of the names that I'm going to use throughout the course. Okay, so yes, we are going to have a very quick trigonometry review, and I think it will be fine with everyone. Next things, understanding the math behind casting rays. Right? So that is the whole point. We're going to use all these ideas of angles, these ideas of casting those rays, and understanding how do we get the distance to the wall? How do we calculate the angles that needs to be calculated to render our projection? What is the 3D projection formulas that we're going to use, right? So we are going to understand everything from scratch. And when I say from scratch, if you ever took a course with me, you know it is from scratch, right? We are not going to write any line of code that we really don't understand everything that is going behind it. Of course, right? We are going to start the actual implementation of our raycasting game. So we're going to start coding, we're going to use a programming language, and we're going to code the player movement and the map grid. So remember when we spoke about that 2D visualization of the world? We're going to start drawing the map and drawing our player move around. So this is something that we're going to start doing in the early parts of our course. And then we have this whole idea of a 2D visualization, right? We have this top view of our player movement and the walls and the rays being cast. And from that idea, right, from that 2D idea, we are going to code this 3D projection where we're going to actually have this little animation of our walls being rendered on the screen. Right, so quick review of what are technologies that I'm going to use. You will see that I'm going to divide this course in two parts, right? This is super important. I'm going to divide this course in two parts. So the first part, I'm going to use JavaScript, right? It is not my favorite language, but it is going to be very good to create a very quick prototype, right? It's not going to be the final implementation. It's just a prototype because I want to get the mathematics out of the way. Right? So player movement, casting the rays, rendering the walls, we can do that thing with JavaScript. And JavaScript is good because it's for prototyping, it's super fast, right? We don't have to think about memory details. How much do I have to allocate in memory? Is this 8 bits variable? Is this variable 16 bits, 32 bits? How do we represent colors? JavaScript is very simple. We don't have to even worry too much about data types. So I'm going to use in the first part of the course, JavaScript, right? So that is going to be the first idea. We're going to get a functional raycasting engine using JavaScript using our browser. So JavaScript is going to be the first part of the course, and in the second part of the course, then I'm going to use a proper language, right? I'm going to use a C. C is very good because it forces us to think about the low-level details of things, right? So we are going to use C, we're going to evolve from JavaScript to C, and in the C implementation, we are actually going to use textures, we are actually maybe going to use shading effects, lighting. So in the C implementation, we can really squeeze more performance out of our engine, right? So first part of the course, JavaScript, right? And then to actually evolve and create a full feature RayCasting engine with textures, with all this maybe optimization details, right? We can look at optimization details for C. Then we are gonna use the language C, right? One of the main motivations for using C is because C is very portable, right? When I say portable is, you can basically get that code, that algorithm, and port to any language that you want, right? C is very generic, so you can port to Swift, you can port to C++, you can port to Java, so then you can go from C and evolve to whatever path you want to follow after this, okay? So hopefully you are on board with my plan. This is going to be the roadmap that we're going to follow, right? So going from the very basic beginnings of the mathematics, understanding the implementation, player movement, coding the map, creating a 2D view, creating a 3D view, starting with a very simple JavaScript prototype, just so we see something on the screen very quickly. And then after that, we evolve and we actually go and we have a second part of our course, where we really start squeezing and getting a full feature rendering engine using C. Okay, so that is the plan. Hopefully you are on board with what I have in stock for us. In the next lectures, we are going to start talking about the actual reviews. We're going to start looking a little bit in the history and kind of dissecting this whole algorithm of how we're going to cast these rays and get our 3D pseudo projection out of the way and seeing something amazing on the screen. So without further ado, let's dive in and let's start coding our ray casting engine.